Okay, so good morning, everybody. Hope you're doing all right. We are a little bit thin on the ground today. I don't know who we've lost. I have the impression we've lost some people in a black hole. Maybe just a black hole bistro. But the H bar, yes. Actually, the bar used to be named the H bar. I don't know if they still...
Oh, really?
Yeah. It's an old joke. No, sorry. About 10 years old joke. Physicists are not very original in their jokes. Okay. Okay, so last time we discussed the Einstein equations. And if you remember the argument, the argument was, let's make any symmetric tensor we can out of the geometry. And there was R mu nu and G mu nu R. And let's set that equal to the stress energy tensor of the matter. And then we fixed this coefficient by arguing that since we'd like the right-hand side to reduce to the stress tensor in flat space-time, which is conserved, d mu t mu nu is 0. The simplest thing to do is to assume that there's some stress tensor which is conserved in curved space-time. But if that is true, then we must make sure that the left-hand side satisfies. So we chose this. We must make sure that the left-hand side also satisfies stress tensor conservation as the combination satisfying d mu G mu nu equals 0. Okay, because we argued that the RHS should obey d mu t mu nu equals 0. So I didn't prove that this combination satisfied conservation. I didn't prove that. So what we want to do is prove that now, that d mu R mu nu minus a half G mu nu R equals 0. So this turns out to be a completely general statement in any geometry and dimension. And so let us now prove it. So the proof relies on an interesting identity called a Bianchi identity. Which I guess was discovered after Riemann. And so it begins by recalling that if we wrote the Riemann tensor with lowered indices, this was a half G nu sigma rho mu minus G rho nu sigma mu minus G mu sigma rho nu plus G rho mu sigma mu plus gamma terms. Okay, so we already showed that just by calculating it. That the Riemann tensor depends on second derivatives of the metric, and this statement is exact. So now let's consider taking the a derivative of this equation, r sigma rho mu nu semicolon eta. And the semicolon is shorthand for covariant derivative. So we write A, comma, or let's say some index mu, comma rho. This is defined to be d by dx rho of A mu. And similarly, A mu semicolon rho is defined to be covariant derivative d rho of A mu. Okay, so the semicolon is traditionally used for the covariant derivative. And what Bianchi discovered is that if you take a derivative of the Riemann tensor, okay, and then you cycle these three indices, okay, you rotate the three around, just the last three indices, that combination is 0. Okay, so let's just write down those three combinations. So it's sigma rho, eta, mu, semicolon nu. I just brought the eta to the front. And then plus r, sigma rho, nu eta, semicolon nu. Okay, so now I'm going to use the locally flat trick to write down these expressions. So in locally flat coordinates, the connections all vanish. But here I'm taking a derivative. Okay, now obviously the connections, the 4 connections associated with all these indices, they're all going to vanish. But when I take the derivative here, I'm going to get third derivatives of this expression. Okay, and then I'll get first derivatives of the gamma. But fortunately, even if I get a derivative of gamma, it's multiplied by gamma, and that's 0 in locally flat. Okay, so everything goes away except the third derivatives. Right, it's a nice argument. So this is equal to g nu sigma rho mu eta. These are now ordinary derivatives, minus g sigma nu. So now I'm going to get a sore hand. And you can probably see this more easily than I can. And spot any errors that I make. So here I'm going to get plus a half. And now I do the cycling thing. I'm just going to write the indices down. Rho eta nu minus rho mu sigma eta nu minus eta sigma rho mu nu plus rho eta sigma, rho, that's wrong. What do I do here? Mu goes to eta. Nu goes to eta. Nu goes to mu. Mu. And must be nu. It goes to nu. Okay. And then we have plus a half eta sigma rho nu mu minus rho eta sigma nu mu minus nu sigma rho eta mu plus rho nu sigma eta mu. Okay, so people in the 19th century didn't have the internet, and so they wasted their time shuffling indices around. But it wasn't a waste of time, because they discovered some very nice identities. And if I did this right, we should see that miraculously all these terms cancel. Okay? So this guy cancels with that guy. Everything is symmetric. The partial derivatives are all symmetric. So the last three indices are completely symmetric. The metric is completely symmetric. This I haven't even written down. Plausibly, right? Rho, this should be rho mu. Rho mu, so this guy cancels with this guy. Eta sigma cancels this one, cancels with this one. Rho eta cancels with this one. Mu sigma, this guy cancels with this one. And I did make a mistake. That should have been rho mu. Somebody should have rho mu sigma mu eta. And this one cancels with this one. Voila. Okay. So this combination equals 0. So first, we only proved it in locally flat coordinates, but that's good enough because any tensor equation which is good in one coordinate system is good in any coordinate system. We only proved it at one point, but if it's true at one point, it's true at every point. So, nice argument. And now what we do is use it. Okay, so we have sigma rho mu nu colon eta plus sigma rho eta mu nu plus r sigma rho nu eta mu equals 0. Okay, that's the Bianchi identity. And yes?
What's the shorthand notation for cycle permutation of indices? Are there like square bracket or something?
Yeah, I don't know. No, square bracket is symmetric. Completely symmetric. Sorry, completely anti-symmetric. Yeah. There's some shorthand notation that this guy is 1/2 f mu nu minus f nu mu, right? So this means all permutations with a minus sign for the odd permutations. This one with symmetric means all permutations with a plus sign for permutations. Okay, neither of them are cycles. Okay, so these are not cycles. I don't know what the notation is for cycles. I just say plus cycles.
You will get cycles if you interchange one of the...
Only if it's anti-symmetric.
Yeah, if it's anti-symmetric. Yeah.
Yeah.
But here...
yes, it is anti-symmetric on these two indices, so yes, that is actually true. We can write this. Because this is anti-symmetric on these two indices, we can write this as sigma rho mu nu eta. No, it should be the symmetrized. You totally symmetrize. Wait a second. No, that's going to be 0. Sorry. The statement is if it's totally anti-symmetric. No, I don't agree. I respectfully disagree. Okay, you have to write it as plus cycles. What is true, we saw this before, is that if f is anti-symmetric, and if I write this plus cycles, okay, this is equivalent to epsilon mu nu, this is ordinary derivative, rho sigma d nu f rho sigma equals 0. Right, this was in Maxwell's theory. So there's a relationship between the cycle thing and the totally anti-symmetric thing, but it's nothing to do with these guys. Okay, so now we have this Bianchi identity. Let us try to reduce it. So let's multiply it with G sigma rho. Okay, so what I'm going to do is get various contractions of the Riemann tensor and derivatives of the which will give me the Ricci tensor. And so obviously, now a very important point, we have already discussed that G mu nu semicolon rho equals 0, right? The covariant derivative of the metric is 0. Similarly, the covariant derivative of the inverse metric is 0. So when I write this inverse metric here, I can pull it inside the covariant derivatives. Okay, there's no, these covariant derivatives do not affect the metric at all. And so when I pull it inside, contracting, I'm going to contract the first and the third index. That's how I get the Ricci tensor. And so what I'll get is R rho nu comma eta from the first term. From the second term, I'm contracting sigma with mu, the first with the fourth. But Riemann is antisymmetric on the third and the fourth. So I can write this as minus R sigma rho mu eta mu. Okay, and when I contract that guy, I get minus the Ricci tensor with rho eta semicolon nu. And then the last term isn't a Ricci tensor, it's some kind of divergence, rho nu eta colon sigma, okay, equals 0. So this is another identity relating Riemann to Ricci, derivatives of Riemann to divergence of Riemann to derivatives of Ricci. And now it's very tempting to multiply this by G rho nu, and in which case this turns out to the Ricci scalar. And now, of course, it's, well, I'll write covariant derivative. That's, for a scalar, that's the same as the ordinary derivative, but let's just leave it as a covariant derivative. And this one, I'm contracting rho with mu, so this is a divergence. R rho eta semicolon rho. And here I'm contracting rho with nu, so this again, I use the fact that Riemann is antisymmetric under the first and second indices, so if I'm contracting the second with the third, that's the same as flipping the second to the first, contracting the first to the third, and getting Ricci with a minus sign. Okay, so this gives me R Ricci scalar sigma eta semicolon sigma equals 0. So we've got a divergence of the Ricci tensor, two terms like that, and they're identical actually, and we have this gradient of the Ricci scalar. So what I can write this as IE, let's put the Ricci tensor first, R rho eta. See, I can raise and lower indices in this equation with G's because they go through the derivatives, okay? So I can just raise the eta index, and I can write this as rho eta semicolon rho, and these two terms are identical, so I have a factor of 2, divide by the 2, and I'll get minus 1/2. I'm going to write this term in the following way as R G rho eta semicolon eta. That should be rho. Let me see. G rho eta semicolon rho. That's right. Because this metric raises the so take this equation, raise the eta index. Okay, that's the same as this equation where the rho, the metric here raises the eta index. So this equals 0. But of course, that equation is exactly what I want. That's rho eta minus 1/2 g. That's the Einstein tensor. G rho eta, which is defined to be R rho eta minus 1/2 G rho eta R. Okay. Semicolon rho equals 0. So that's what we wanted. Okay, any questions about that? Now I want to give you another derivation of the Riemann tensor, which is also gives you a new insight about it, and is very useful in practice in many applications. Another derivation of Riemann. And again, it comes from the geodesic equation. It's called the equation of geodesic deviation. Okay, so the idea is extremely simple. I've got some geodesic curve, x mu, and let's pick it a proper time, tau. So let's think about a massive particle. So the geodesic equation we're going to use in its affine form, or equivalently, you can think about this as a photon with an affine parameterization of its geodesic. So I've got one geodesic, and let's consider another geodesic, which is nearby. Okay, so this geodesic will be x mu of tau plus delta x mu of tau. And at any fixed tau, the difference between the two is delta x mu. Okay, so that is the geodesic deviation. So this is a very physical thing. I can imagine sending two particles through space, and they measure the distance or the displacement vector, x mu, between the two of them, and see how it changes. In a gravitational field, this displacement will grow because of the presence of the gravitational field. They're both going to respond differently since they are at slightly different places. So the equation of geodesic deviation. Now, what is this equation? Well, the displaced trajectory obeys this equation, x mu plus delta x mu plus gamma mu nu lambda. Again, let me follow the convention that, those really do have an index. I'll follow the convention that the arguments I don't put indices on, just not to confuse matters. Okay, so this really is 4 coordinates, but I'm not going to put the indices. So we just have to keep that in mind. And then x mu plus delta x mu. This is a nu, and d by d tau of x lambda plus delta x lambda equals 0. Okay, so that's the equation for the second geodesic. And of course, I have the equation for the first geodesic, plus gamma mu nu lambda dx nu d lambda, d tor, dx lambda d tor equals 0. So I have these two equations for the geodesics, and the obvious thing is to take the difference between them and and keep terms linear in delta x. Okay, so if delta x mu is small, then the difference between these two equations is this equation, which is d2 delta x mu d tau squared. This gamma is not the same as that gamma because it's evaluated at a different place. And so all I need to do is to keep the first order term. And so this will be delta x rho gamma mu nu lambda comma rho dx nu d tau dx lambda d tau. Okay, so that's from differencing this term where I took to first order in delta x, and I subtracted this term. And then I have these terms too. So I have plus twice, two of them, gamma mu nu lambda dx nu d tau d delta x lambda d tau. Okay, equals 0. So that's the equation for the geodesic deviation. It's a correct equation, but it's a bit of an ugly equation because, this will be interesting, okay, the middle. Sorry, I'll keep this one here, it's fine. So it's a bit of an ugly equation because it's not a tensor equation at all. Okay, so let us try and construct a tensor equation. And let's try to make this into a tensor equation. And the obvious problem is that even the first term isn't a tensor, right? We proved that the second derivative of the d by d tau derivative of a vector is not a vector because it doesn't transform like a vector. And so we should really be using d, capital D by d tau, covariant derivative along the curve of delta x mu of tau. And so what is this equal to? Well, it's covariant derivative, d by d tau, of the covariant derivative right? That was the definition of a covariant derivative of some quantity, some vector. Delta x mu is a vector. The covariant derivative of the vector along the curve is given by this. Now I have to work out the covariant derivative of this. Okay, so that again is just the ordinary derivative, d by d tau times the stuff in brackets, plus gamma mu nu lambda, and I put the curve here, the tangent vector here, and I put the stuff in brackets there. Okay, so I just have to work all this out. So the first term is d by d tau of that stuff, and that gives me d2 by d tau squared delta x mu. Then I've got to take the d by d tau derivative of these terms. Taking the tau derivative of gamma, I differentiate gamma with respect to x, and then I multiply by dx d tau. So I get plus gamma mu nu lambda comma alpha dx alpha d tau. And then we have delta x nu dx lambda d tau. Okay, so that's coming about by differentiating the gamma. Now I have to differentiate the delta x. So I have plus gamma mu nu lambda d delta x nu d tau dx lambda d tau. And then, of course, I've got to differentiate the dx d tau. So plus gamma mu nu lambda d delta x nu d2x lambda d tau squared. Okay, so I've now worked out this first term. So this term is the same as these three terms. And I've got to add in the last term, the second term, and that is plus gamma mu. Let me use some new indices here. Alpha, beta, and alpha, beta. So gamma mu alpha beta d by d tau of delta x alpha dx beta d tau, and then we've got plus gamma mu alpha beta gamma alpha nu lambda delta x nu dx lambda d tau dx beta d tau. Front, middle. Okay, so this term became that last term. Now, one thing I know in this equation is this d2x d tau squared, because I had the original geodesic equation. And so this term right away I can write down as this equals minus gamma lambda alpha beta dx alpha d tau dx beta d tau. Okay, so using that, so I've used that. Now this one, I can eliminate using the very first the last equation on the top blackboard. Okay, so if I bring that one down, let's call this one star. Okay, so this is using star. I can eliminate the d2x d tau squared. So this is going to give me minus gamma nu lambda mu comma rho delta x rho dx nu d lambda dx lambda d tau. And then it's going to give minus 2 gamma mu nu lambda dx nu d tau d delta x lambda d tau. And so we're getting things like Riemann, right? Because here I've got a derivative of gamma. Here I've got a derivative of gamma. Here I've got a gamma-gamma term. Here I have a gamma-gamma term. Okay, so it's looking good. And so I can write this as minus gamma mu nu lambda comma rho of delta x rho. Let me do x dots just to save a bit of time. X dot nu, x dot lambda. So x dot lambda is dx lambda d tau plus gamma mu nu lambda comma alpha x dot alpha delta x nu x dot lambda minus gamma mu nu lambda gamma lambda alpha beta x dot alpha x dot beta delta x nu plus gamma mu alpha beta gamma alpha nu lambda delta x nu x dot lambda x dot beta. And hopefully I have got everything. So now I'm just sorry, did I minus 2 plus. So let's just check the other terms cancel. So this term certainly cancels with this, right? There's a minus 2, there's a plus 1. And somewhere else I should have a similar term, this term, right? So let's just draw those in color chalk. This one, and this one all cancel. Okay, leaving me with the two derivative of gamma terms and what happened to this? Oh, yes, and this gamma term, right, and this gamma term. Okay, so that's everything. So what is it equal to? Well, it's obviously equal to the Riemann tensor mu nu lambda rho x dot nu x dot lambda delta x rho. So that's a nice equation. It's telling you that the rate of change of the displacement of two geodesics, the acceleration in the displacement of two neighboring geodesics, the acceleration of the displacement is given by the Riemann tensor. Okay, so now in practice, if you're going to measure the strength of a gravitational field, that's the only thing you can measure, because your velocity doesn't really mean anything. You can always pick a frame in which your velocity is 0. But the acceleration, you can't pick coordinates to make the acceleration 0. And the reason you can't is because of the Riemann tensor. So this is the test of whether there is really a gravitational field. Present. And so just before answering, let me just mention there's a theorem. The theorem is the following. I think we have We've not quite done enough to prove it, but we have almost proved it. It is proven in Weinberg's book, in Stephen Weinberg's book, is that if the Riemann tensor nu lambda rho, so the Riemann tensor equals 0 at every point in space-time, this is a necessary and sufficient condition for there to exist coordinates in which g mu nu equals eta mu nu for all x. Okay, so if the Riemann tensor is 0 everywhere, the space is flat. In the right coordinates, you would just see that the metric is eta. Okay, that's a theorem, and then there would be no gravitational forces at all. Yeah?
Please repeat why that is a test of whether there is gravitational force.
It's a test because if you consider a geodesic, so this particle is in free motion in the gravitational field. The whole, I mean, this was Einstein's insight, is that if I have, okay, let me see if I can say it. Yeah, so Einstein's insight was that, imagine I have some particle falling in a gravitational field. If I pick coordinates in which the particle is at rest, and if the gravitational field is constant, so that the acceleration is constant, I can choose coordinates in which there's no gravitational force at all on the particle. That was the equivalence principle. Okay? So the picture is the following, that imagine we have a completely uniform gravitational field. One viewpoint is that the particle is falling and you say it's being accelerated by gravity. The other viewpoint is to enclose the particle in a box and imagine you are an observer standing in the box and the box is falling under the gravity. Well, the particle just stays where it is. There's obviously no gravitational force. Okay, so this person sees no gravity at all because they're falling with the particle. The only way to see that there is gravity is if the gravitational field changes from one place to another. So, for example, if the situation is not this, but imagine we have a black hole, or imagine imagine it's the Earth, but we're some way away from the Earth. And our box looks like this, but the box is a finite size, okay? Could be this box, but it's a finite size. So now I have two particles. Well, one of them is going to fall each one will fall towards the center of the Earth. And you're just falling down with the coordinates. So you let the two particles go, and what you see is they start moving together. Okay, well, that's a consequence of the Riemann curvature. Okay, so such a field, this field has a non-zero Riemann curvature, and the deviation of the two particle trajectories, of the two free particle trajectories, is non-zero. So even if I set the particles at rest in my box, there's no gravity because they seem to remain at rest, but I notice they start pulling together, and that's because of the Riemann tensor. Okay, any other questions? So now we're going to get on to...
Sorry, about, or just a comment about that, because I've seen that box before where the two particles start moving together, and it's occurred to me a couple times, and I don't really, I'm not really good enough with a lot of this math to work it out on my own, I think, yet. Maybe hopefully after this class I might be, but we always deal with test particles that don't have any gravitational attraction of their own.
Yes.
But of course, if we take this box way out into the middle of empty space where it's not near any gravitational field and we leave them there,
Yes.
they will eventually start to move towards each other because of their own mutual gravitation.
Right.
And I'm wondering if there's any.
But that's not the same. That's a different effect.
I know it's a different effect, but I'm wondering if there's like how you can show that it's a totally different effect.
Well, just the magnitude of it. Okay. So, you know, the metric for the Earth, let's say. Okay, so the line element, remember, was 1 minus 2 gm over r c squared minus this dt squared and the other terms, right? And so this was the 2 phi over c squared. So the Riemann tensor is the second derivative of the metric. So the magnitude of it would be gm over c squared, two derivatives of this, so it's r cubed. That's the strength of the Riemann tensor. Okay, so when you work out in this equation how fast are these particles going to come together, it's going to be governed by this parameter. It'll be very slow because you're a long way away from Earth. So this will be a small number, but this will determine the d2 by d tau squared. The acceleration. So basically we've got an equation that delta x times r will be d2 tau squared delta x. I think I've lost, let me just see. No, that's okay, yeah. I'm worried about my C's always, but you see these guys are, okay, let me just, no, that's fine, the dimensions are the same. Yeah, so it's going to be, the dominant term is actually going to be the r00 here, because this velocity in time, full velocity in time is the biggest component. And so what that means is that there's actually a c squared here, because remember x naught equals ct. That c squared cancels this c squared. And so it goes like the following. Yes, I think that is hopefully the right dimensions. So basically the rate at which these particles converge is determined by an expression which you could have worked out in Newtonian gravity. There's no particular relativistic effect here.
Independent of the particle masses.
Completely independent of the particle masses.
So you could prove that this was different from
yes.
mutual gravitation by like taking a limit as their masses go to 0 and saying that their action
doesn't compete with this one.
Right.
In that
Don't we usually have, like, I mean, whenever we talk about geodesics for test matter, that we usually consider them to be representative of some congruence, where we do take into account what the back reaction is, as in that's where it's, I mean, for the energy conditions tell us what the curvature is beforehand for the congruence. And we say that this holds for any two representative geodesics of that congruence. So what Ben was talking about...
We don't take the back reaction.
What is that word you're using?
No, not here. Not here.
That's
because these are just two representatives of those, so we don't have to worry about it.
You could say that, or you could just say it's empty space.
What he said was that if you have these two really then you're again saying that these are point sources, and then we start giving you the stress tensor, and then that is actually back reacting.
Yeah, that's
so it's going to source the curvature again.
No, that's actually true.
So that's why it's easiest to think about it as representatives of the congruence a priori.
In which case they're
it's
a small component. Well, the only thing I don't like about that is that this is an empty space. These are the only two particles there. Okay, so we're in empty space. We're in a solution of the Einstein equations, which is a vacuum solution. We put these two particles in, they hardly change it. I mean, what you're saying is that the way in which the two particles attract is that actually their mass causes space-time to bend around them. So this metric was wrong. This metric has another correction, which depends on g times the mass of the particles. Okay? And yeah, so we would really have to compute the metric for 2-point masses.
Yeah.
outside the metric, and then that would come into the Riemann tensor and determine their motion. So, yeah, you're absolutely right. Okay, so, but it is a very different effect. Now, we're going to do something very fun now. Unfortunately, like everything in GR, lots of algebra. Okay, but the results are amazing, like everything in GR, which is to compute the metric of a black hole. And then next week we're going to think about this black hole and what it means. In fact, we've got one more day this week, so we're going to do the geodesics in the black hole metric tomorrow, and then we're going to try and understand what they mean next week. So actually what we're going to do is a sort of full derivation of this line element. So far I really just talked about G0 and the perturbation to G0, and we saw that a little bit of G0 acts like a Newtonian gravitational potential. I didn't talk about all the other components of the metric at all, and because of that we can't really calculate anything yet. So we have to solve the Einstein equations. So let us solve. So let's write it this way. The simplest solution, this really means a solution of the Einstein equations apart from flat space. So imagine you're a mathematician. Your name is Schwarzschild, okay? And Einstein has just come out with these crazy, horrible equations for a metric. Now, Schwarzschild, I believe, was in the middle of the First World War, okay? So he was in the army, and he's sitting in some hut in the middle of a dirty field somewhere, and all of his friends are being killed everywhere around him. And you can't blame him for wanting to focus his attention somewhere else. And so he focused his attention on these equations. He said, let me try and find the simplest solution I can to these equations. Okay, and that is the Schwarzschild solution. Of course, simplest is a bit subjective, but so Schwarzschild says, okay, I'll take Einstein's equations and forget about the matter. Obviously, matter in the universe is localized in lumps. Everywhere in between, there isn't any matter. So it's pretty interesting to see what is the curvature of space and time in between the matter. And so he's just going to solve G mu nu equals 0. Are there any non-trivial solutions of this equation? Now, G mu nu is R mu nu minus 1/2 G mu nu R equals 0. But if this equals 0, I can take the trace of this equation. I can multiply it by G mu nu. That must be 0. The first term, so this is equal to R. This term, now what is G mu nu times G mu nu contracted? What is G mu nu, G mu nu? It's 4, right? Because G mu nu, G mu alpha is delta nu alpha. And delta alpha alpha just means you sum the alpha from 1 to 4. So this is equal to 4. So what you get is R from this term, and then minus 2R from that term. And so I conclude that R equals 0. So in the absence of matter, stress energy, the Ricci scalar is 0. So that simplifies everything, because then the Einstein equations, so for T mu nu equals 0, i.e. outside any matter, okay, in the space between the stars, well, let's say it's really in the, yeah, okay, it's outside any matter. Einstein equations read Einstein's equations read R mu nu equals 0. So Schwarzschild says, well, is there any non-trivial solution of that equation? And if you're a mathematician, it's very reasonable to impose some symmetry to make the problem easier. And in particular, let us choose spherical symmetry. So that makes sense because, after all, the sun is pretty nearly spherically symmetric. We try to think of what is the sun's gravitational field outside of the sun. It's reasonable to approximate it as spherically symmetric. So let us assume spherical symmetry. E.g. the sun. Of course, it's important to realize that nothing in the world is really spherically symmetric in the universe. So this is it's only an approximation for the sun. It's a pretty good approximation for the sun. This all becomes really interesting when we talk about black holes. No black hole is going to be spherically symmetric. Okay, so the Schwarzschild solution, even though it is everywhere in the textbooks and everyone learns it as the description of black holes, it is not what a realistic black hole looks like. Realistic black holes have angular momentum at some level, and they are the Kerr metric. And they're much more interesting and have all sorts of bizarre phenomena inside them. And I hope we'll spend at least a lecture on the Kerr metric next week. But anyway, you're Schwarzschild. You're at the beginning of this subject. So it's totally reasonable to assume spherical symmetry. And that means that the metric can depend only on rotational invariant, well, let's call it the line element. The line element can depend only on rotational invariant quantities. Okay, there's no special direction, spatial direction at all. So instead of depending on t and x, which a general metric would do, this only depends on it only depends on a subset of quantities. It depends on t. It can involve dt. These are obviously rotational invariant. It can depend on r squared, which is x dot x. Okay, so by assumption, I'm saying there's a rotational symmetry. Remember what rotational symmetry is. Rotational symmetry is a transformation that x prime goes to some rotated version of x, where O is a rotation matrix, but the distance is invariant. From this equation, we have r dr. That's also rotation invariant. And of course, we can write down dx squared, which is dr squared plus r squared, d theta squared plus sine squared theta d phi squared. Okay, so given a set of coordinates t and x, and given a rotational symmetry, x prime goes to ox, these are the only things I can write down which are invariant under O. That's a complete set of things. There's nothing else you can write down. So the metric can only depend on these quantities. And so we can write down straight away that the line element is minus, and so C of R and T is an arbitrary function, dt squared plus E of r and t dr squared minus 2d of r and t dt dr. Okay, so this part of the metric, the time involving dt and dr, has all components. Only constraint is symmetry, that the coefficient of, that there's some coefficient of dt dr. If you view this as a matrix, this would be minus c e minus d minus d. This would be the tr components of the G mu nu viewed as a matrix. And then I have f of r and t, some other function, times r squared d theta squared plus sine squared theta d phi squared. Okay, so that's the most general thing you could write down that has a spherical symmetry. Okay, this expression, if I define the x as a column vector, r sine theta cos phi, r cos theta sine phi, r cos theta, the metric is invariant under rotational symmetry. So this is the most general spherically symmetric metric. But you can simplify it because we are free to choose different coordinates. So in particular, that off-diagonal, well, we can immediately get rid of several of those functions, of two of those functions. Let's begin with this function f. So first of all, we can remove f by defining r prime equals root f of r and t times r. Okay, so the coefficient in front of the angular term is f times r squared. Well, let's just call that r prime squared. Okay, this is a coordinate transformation from r and t to r prime. And if you want, we can write this too. That's a valid coordinate transformation. And in the t prime r prime theta phi coordinates, there f equals 1. F is f equals 1. So that's very easy. We've just picked new coordinates. By the way, those are kind of nice coordinates because what it means is that the area of a sphere in those coordinates, you see, when I go around a sphere, all I change is theta and phi. And if the line element is this, okay, with coefficient 1, this means that the area of a sphere equals 4 pi r squared in these coordinates. So by choosing your radius in this way, you're ensuring that the area of a sphere, even though the space is curved, the proper area of a sphere is 4 pi r squared. Okay, so that's the first simplification. And so now we're going to try and get rid of the term d, remove d of r and t by setting with the following trick. dt prime equals to some function of t and r. So I'm going to redefine the time coordinate. So by the way, let me just say, I'm going to define these new coordinates and then drop the primes. Okay, so this is a coordinate transformation from my original ones to some t prime and r prime. I'll get my new metric in the t prime and r prime coordinates. This should really be r prime, okay? But then I'm going to drop the primes. So now I just have my original metric, but with f equals 1. So now I'm going to get rid of d by redefining, by defining some new time coordinate, t prime. And it's going to be c dt defined by this equation, c dt plus d dr. Okay, so the reason for doing that is that you can see that the dt squared term, if I the combination of the dt squared term and the dt dr term are the first two terms in the square of this guy. Okay, so if I define this new time that way, it already includes the cross term without needing a cross term. Okay, so in the dt prime coordinates, the cross term will go away. And I'm free to include this overall factor because that will just emerge as a factor multiplying the dt prime term. In other words, it can be absorbed into the c. Okay, so this is a good way to try to eliminate the cross term. And the question, so this function f is completely free in this transformation. It is determined by the fact that this must be a consistent coordinate transformation. So if there is a function t prime of t and r, then it follows that dt prime is dt prime dt times dt plus dt prime dr times dr. Okay? But if that's true, then dt prime dt is this guy, and dt prime dr is that guy. And then you've got to have equality of mixed derivatives. Okay? So this means that dt prime dt is f times c, dt prime dr is equal to f times d. And necessarily, we must have d2t prime dr dt is d2t prime dt dr. And this gives us an equation that d by dr of f times c must equal to d by dt of f times d. So in order for that coordinate transformation to exist, we must have f has to satisfy this equation. Now, it's not hard to see that the solution does exist. An easy way to see it is that, so c and d are some given functions of r and t. I want to see, is there an f such that this equation is true? And the way to see it is to notice that this is like a time evolution equation. That given, so if I think of t as one axis and r as the other, given this function at t equals 0, I can work out its derivatives. I can work out the derivative of the right-hand side. And this will tell me the first time derivative of the function at t equals 0. Okay, so this equation, so given f, f at 0 and r, this equation will give me d by dt of f at 0 and r. But likewise, I can differentiate it again with respect to t, and I can get f double dot in terms of f dot and f. And I can get f triple dot in terms of f double dot and f dot and f. And I can just iterate this. So I can work out the Taylor series expansion of f in t around t equals 0. There's some arbitrariness in f, which is this initial function of r, but the equation completely determines all the time derivatives of f at t equals 0, and then by Taylor series, I can get the function. So locally, there is always an f such that this is true. Once you have that f, you can do this coordinate transformation. And if you do that coordinate transformation, you are, so the metric, d, we can just see by substituting, ds squared will be minus, 1 over f squared times times dt prime squared. I better divide it by c so that I get the right coefficient for the dt squared term. Now I'm going to get a cross term, which is let's work this out. I hope this works. Minus, so this term amounts to c dt plus d dr squared over c. So if with a minus sign. So if I work it out, I'm going to get minus c dt squared from the first term. The cross term will be minus 2cd over c. So I get minus 2d dr dt, right? And then I get minus d squared over c dr squared. So I need to add back plus d squared over c dr squared. And I already had a plus e dr squared. And then I had everything else, plus r squared d theta squared plus sine squared theta d phi squared. Okay, so I've shown that the original metric is equal to the new metric, but with no cross term. I just had to redefine the time. And now I'll just redefine all of this to be a. This is going to be some other function. So in the new coordinates, again, just dropping the primes, ds squared a of r and t d squared plus b of r and t dr squared plus r squared d theta squared plus sine squared theta d phi squared. Okay, so what we've done is we had a lot of freedom in redefining r, which was spherically symmetric, and t, which was spherically symmetric. We used the r freedom to set this coefficient equal to r squared, which geometrically means the area is 4 pi r squared in these coordinates of any sphere at radius r. And then we use the t freedom to remove the cross term. But we're still left with these two arbitrary functions. Okay, so these are still arbitrary. So in these, so in these coordinates, if you think about what the object looks like, basically, if one coordinate is t and the other one is, maybe I'll draw it like this. Here's t, here's r. R is this radial coordinate. And what the metric looks like is that it's symmetric under rotations. So this is r equals 0. The metric is cylindrical. Okay, so I can rotate it outside in the other directions, in the theta and phi directions. And it's completely spherically symmetric. So at fixed r, it looks like this. And the area of constant r surfaces in space is 4 pi r squared. So that was a big simplification. Now you only have to solve for these two functions, a and b. But this general problem, you see, we had to fix coordinates. We've got a lot of coordinate freedom in general relativity. Whenever you solve anything, you have to face this problem of how do you fix those coordinates? Which coordinates are the most convenient to use? They're all equivalent, but you have to decide which ones are the most convenient. So now we're just going to do some algebra and calculate the Riemann tensor and then the Ricci tensor. And I would advise you to actually work through this yourself, just to convince yourself that everything is here. Once. Do it once on paper. Okay, it'll undoubtedly be wrong. I hope my answers aren't wrong. But I'm sure if you do it, you'll get the wrong answer the first few times. And then there's a rather nice software package which is on Jim Hartle's website. So if you look up James Hartle, so he wrote a nice undergraduate textbook. He's the Hartle of Hartle-Hawking. He wrote a nice undergraduate textbook on relativity. It's more elementary than this course. But if you look on his website, he's got a little software package for Mathematica, and you just stick in any metric, and it'll give you all the tensors you want. So that's worth playing with. And then if you ever do anything in GR, you'll have this high-tech way of calculating all these quantities. But I do advise you to check this yourself. Okay? So for this metric, okay, so here we obviously have G mu nu is a 4x4 matrix minus a 0, 0, 0, not so many zeros, B 0, 0, 0, 1, 0. Actually, no, this is r squared. This is r squared sine squared theta, 0, 0. So here's my 4x4 matrix, which is G. And now you can calculate the connection symbols from the formulae I gave. This is a dot over 2a. I'm going to define dot to be d by dt and prime to be d by dr. And now we just have to do this really boring calculation. Totally straightforward. except you have to get it all right. 2a. Okay, so remember the gamma is just given by the half g and then g terms. First derivatives of the metric. Then I have gamma r tt, a prime over 2b, gamma r tr is b dot over 2b, gamma r equals b prime over 2b. So gamma r theta theta minus r over b, gamma r phi phi equals minus r sine theta over b, sine squared theta over b, gamma theta r theta is 1 over r, gamma theta phi phi equals minus sine theta cos theta, gamma phi r phi equals 1 over r, gamma phi phi theta equals cot theta. Okay, with others, with the other components given by symmetry. By symmetry, I just mean the fact that it's symmetric under the lower two indices, or equal to 0. Okay, so everything that's not determined by symmetry here is equal to 0. So it's not really that bad. But one can imagine Schwarzschild slaving over this and trying to get away from the real world. And now, of course, we're not done. We've got to get the Riemann tensor. And then we've got to contract the Riemann tensor to get the Ricci tensor. And essentially all that amounts to doing is multiplying gammas and taking first derivatives of gammas. And when you've done that, you will get this formula. I can promise you it'll be worth it. It looks terrible, but it is worth it. Then we have RTR. This one's easier. It's just B dot over BR. We have RRR, which is minus A double prime over 2A plus A prime squared over 4A squared plus A prime B prime over 4AB plus B prime over BR minus B double dot over 2A plus A dot B dot over 4A squared plus B dot squared over 4AB. And finally, our theta theta is equal to 1 minus 1 over b plus rb prime over 2b squared minus RA prime over 2AB and R phi phi is equal to sine squared theta R theta theta. So that's it. These with other components are 0. Zero. So these are the Einstein equations for spherical symmetry. Now, even though they look ugly, the consequences are amazing. Okay. So imagine you're going to solve these equations. You're called Schwarzschild. Which equation would you start with? Let's look at that one. That looks a great equation. Okay. So RTR, so B dot equals 0. Okay, well, the first thing it means is that B is only a function of R. It doesn't depend on T at all. And the second thing is even more dramatic, because if B dot is 0, then all the time derivatives disappear. Okay? These terms disappear. Those disappear. And all time derivatives disappear. Phew. Okay. And so now we're going to use the other equations. And the obvious thing to do is to take a combination of this one and this one to make the A double prime go away. So I get only first derivatives in my equation. All these time derivatives have gone. These are second time derivative. So I take a linear combination. I take RTT plus A over B R. And what you find is that this is nothing but A prime over B plus B prime A over B squared equals 0. Because we took a combination to cancel the second derivatives of A. Lots of other cancellations happen. This A prime B prime term goes away. So you just get this term and the A prime squared term cancelled. You're left with this term, and this term. That's all. Okay, but this equation just reads that A times B prime equals 0. And so what this means is that A is an arbitrary function of, it means that A equals 1 over B. A is an arbitrary function of time over B. And if that is true, I can plug it back into this equation. No, sorry, I don't want to do that. Sorry, I want to use the R theta theta equation. If A is 1 over B is a function of T over B, you see the function of T disappears. And so R theta theta becomes 1 minus 1 over B plus R B prime over B squared equals 0. And this implies that R over B prime equals 0. R over B prime equals 1, sorry. And this implies that R over B is equal to R plus constant. And let's call the constant what shall I call it? K, constant. And so this implies that B is 1 over 1 plus K over R. And so A is equal to a function of T times 1 plus K over R. But that's rather nice. Because we're still free to redefine time. And all that's going to happen is that function of t is multiplying the dt squared. So let's just redefine the time to remove it. Okay, so we have this metric which has f of t dt squared. And we can redefine the time to set f equals 1. Okay, that just means that I'm setting f of t dt squared to be equal to dt prime squared. And so voila, we have that ds squared is equal to minus 1 plus k over r dt squared plus 1 over 1 plus k over r dr squared plus r squared d theta squared plus sine squared theta d phi squared. That is Schwarzschild metric. You might guess the k is just minus 2gm over c squared. It's an integration constant. We can identify it with the mass of the body that generates this field. But we've done more than Schwarzschild, actually, because we've proven something called Birkhoff's theorem. Birkhoff's theorem says that the most general spherically symmetric metric is static. And it has to equal the Schwarzschild metric. Okay, so, for example, if I've got a star and it explodes, okay, it doesn't matter the speed, but imagine the sun exploded. It will explode in about 2 billion years, I believe. And we're sitting here, and our sun has exploded, but it's spherically symmetric. Well, we will see absolutely no signal of that until the spherical wave hits us, okay, because this is the metric. That's what it has to be. And there is no, so gravity has this strange property that spherical symmetry kind of eliminates any possibility of detecting a change, which is happening at the source. Okay, sorry I went over. Any questions?
Do we still have the freedom to redefine t? Because we had already chosen t to cancel the cross term. So I'm worried that maybe by changing it again, we'll get back.
You can keep changing coordinates as many times as you like. So we got to a metric with no cross terms, right? We got there. We had minus a dt squared plus b dr squared. Okay, I still have the freedom to say t dt is any. Yeah, I still have the freedom to redefine t in any way I like. All I'll do is multiply this a by some other thing. Okay, so if I determine that a is some function of time, I can what I do is take the square root of this times dt, and I say that that is dt prime. And then, of course, to get t prime, I just do that integral. So this is t prime. And that's fine, doesn't introduce a diagonal term. If I had used an f which depended on r, then I'd create a diagonal term. But because f of t only depends on t, it won't create a diagonal term when you do that final time redefinition. Any other questions? Okay, so we have our black hole. And tomorrow we're going to fall into it. Okay. What?
Are we not getting lunch or dinner today?
We're not going to?
Getting lunch or dinner today?
Yeah, I don't want to encourage you to stay in the bistro. But so that's why I say come here. All right.